Hey guys, this is Dr. Chamberlain. This is an example problem looking at the transition metal complex hexa aqua titanium 3, and this is a calculation-based problem where we're going to be figuring out the ligand field splitting energy, which we can call delta O. For this complex, we're looking for that in kilojoules per mole, and we're starting with the wavelength that this complex absorbs. So this will be a complex ion. If we look at, we have titanium 3+, since water is a neutral ligand. And titanium 3+ is actually going to be, let's get our argon, 3D1. Since titanium starts with 4 valence electrons, so it would really only have 1 electron. There are 6 waters for the complex, so it is an octahedral complex. And I'll have my delta O, and I'll just have that 1 electron. But 1 electron is enough that when a photon comes along, it can excite that electron into an upper level, so from the ground state to an excited state. We are provided with the information that this excitation of the electron from the ground state to the excited state it comes at a wavelength of 510 nanometers. And if I look at my color wheel, 510 is in the green region. Yes. Okay, so I'm looking at an absorption in the region of green. So it absorbs green, so I could expect this complex in solution to appear red if I was looking at this. This problem does not require that I know that it's red, but I wanted to walk you through that since that's something that does apply to other problems. So here we want to know, what will the energy be for delta O? And in this case, that's the splitting energy. It's the energy that this photon that can excite the electron, it's the energy that that photon would have. So delta O, that splitting energy, correlates with the energy of the photon. And the energy of a photon, we may recall, is also on your equation sheet, is equal to hc over lambda. Lambda is the wavelength, h is Planck's constant, and c is the speed of light. So we can calculate that energy using wavelength and these two constants. So just looking up Planck's constant, it's 6.626 times 10 to the minus 34 joules times seconds. The speed of light is 2.998 times 10 to the 8 meters per second. You can tell I live near the train tracks. And we've got 510 nanometers. And actually, I'm going to go ahead and convert that just to simplify life a little bit. I'll keep it in 510, but a nanometer would be the same thing as 10 to the minus 9 meters, since I'm going to want my meter units to cancel here. So let's do a couple of cancellations. Seconds will cancel, meters will cancel, and I can calculate this out. What I get here is that delta O is equal to 3.90 times 10 to the minus 19 joules. Now that's not very many joules. In fact, 10 to the minus 19 is a pretty small energy. But what I have to realize is this is the energy for just one photon, right? This is the energy of one photon coming and doing that excitation, one excitation of one electron just once. So my question was actually asking me for energy in kilojoules per mole. So I need to think about what that energy would be for a mole of excitations, which would mean a mole of photons. So I would take this energy joules per photon, and I would say, okay, I could have a mole of anything, so how would I have a mole times 10 to the 23 photons in 1 mole? And so that would give me now my energy in joules per mole. And I get 2.35 times 10 to the 5. And to get the units that they asked for here, I'll just change that to be 2.35 times 10 to the 2, or I could write scientific notation, or I could just say 235 kilojoules per mole as the energy. So a pretty straightforward calculation. It does require that you put together the pieces, right? We're putting together the wavelength absorbed. That wavelength that is absorbing, the electron absorbs, is the same thing as the splitting energy. And then I'm using the energy for a photon to calculate that splitting energy in kilojoules per mole. So thinking about a mole of photons. So yeah, there's your example. Have a good one.